In this lecture, we are going to now study a very interesting model which is known as the percolation model. Percolation model. And this percolation model, it's actually not a new model for modeling the spreading of your diseases. Rather, it is a new angle, new way of looking at our already existing models, SIR model, SIS model, and for a matter of fact, even for your branching model, simple branching model. We are going to look at these models from a different angle. I'll tell you what is the different angle. So let's quickly see. We'll quickly simulate SIR model on a network, and then we'll see how can we look at it in a new manner. So let's take a network here. So I'll just quickly make a network over here. I'll take some nodes. And we'll take some edges. Let's take some edges. So I think this should be enough. Okay. So we take this network over here. And now we simulate a SIR model on it. And let's say our Ti equals to 1. That is, every node remains infected for one time period. And after this one time period or one day, that node stops infecting other nodes. And let's say the infection starts from this node. So this is our node which is infected at time 0. The 0th day, this node is infected. Then now this node has 4 neighbors and it gets a chance to infect each of these neighbors. So I'm sure that you know how this process is occurring. So each of the edges over here has a probability P of infection. So what we are going to do is toss a coin for this particular edge, and this will be a biased coin such that probability of head on that coin will be P and probability of tail on that coin will be 1 minus P, right? So we'll toss a coin over here and see whether it's a head or tail. If it's head, we'll infect this node, else leave it. Similarly for this edge, and for this edge. And let's say after doing this 4 coin tosses, this node over here and this node over here gets infected. So both of these nodes, they get infected at time t1. Now in the next iteration, both of this particular node, it recovers and it is no longer able to infect other nodes, while these 2 nodes over here, they now go ahead and they infect the network. And let's say that in the next time step, that is at time 2, this node over here gets infected. So this node gets infected at time t2. And then again both of these nodes recover, and then this node over here, it sees and it tries infecting other nodes, and let's say it ends up infecting this node over here and this node over here. So both of these nodes, they get infected at time t3, and then this node has a chance for these 2 nodes now infect further. And let's say that in the next iteration, this node over here gets infected. So this happens at time t4. So how do we view this process? We are viewing this process as there was this time 0 when this node gets infected, day 0. Then it gets a chance to infect its neighbors, and that at time 1, at day 1, these 2 nodes get infected. And then time 2, these 2 nodes get infected, and so on. So we look at this process in terms of time. Now, percolation model asks you the question that, can you remove this notion of time from here? It seems to me to be a very dynamic process. Everything is running dynamically. Time 1, time 2, time 3, time 4. Can you make it static? So let's say I want to know I was having this initial network over there. Okay, so initially my network was like this, and then okay, wait. Okay, and this node over here, this node was infected, and let's say now I'm interested in knowing when this process will run whether this node over here will get infected or not. And then what we did for knowing whether this node will get infected or not, we ran the simulation in terms of time. We looked at what will happen at time 0, what will happen at time 1, what will happen at time 2, and so on. And finally we see that yes, this node over here is infected. There is a very new way, a novel way to do this, a very interesting one, where this process will not run in terms of time. We'll look at it as a very static process, and that is what's called the percolation model. So how do I make this entire process static is, okay, so I'll take this network. So this is my network, and I want to see how I can make everything static over here. This is the network. This is the network I'm having, and wait one second. Okay, this is the network we are having, and then we know that at the beginning this node over here is infected, and we are interested to know whether this node will get infected or not. And we know all this is a complete game of tossing a coin only. At time 1 we have tossed a coin for this. Whatever gets infected, in the second iteration we toss a coin for that particular node. Whatever gets infected in third iteration we toss a coin for that particular node, and so on. Now see what we'll do is, first of all, I'll just quickly label all of these edges. So let's say this is E1, E2, E3, E4, E5, E6, E7, E8, E9, 10, 11, 12, 30. So there are 14 edges in this network. What I am going to do is, instead of running this process time wise, I am now going to flip 14 coins, one for each edge. So first I flip a coin here for this edge E1. So I flip a coin for E1, and let's say I see a tail. And then I flip a coin for E2 and I see a tail. E3, let's say I get a head. E4, let's say I again get a head. E5, let's say head. E6, let's say head. We are getting so many heads. E7, I got a tail. E8, I got a tail. And then let me toss it for E9. I get a tail. E10, tail. E11, let's say head. E12, again a head. E13, tail. E14, tail. Okay. So see, what I am doing is I have flipped a coin for all the edges at the beginning itself. I am not running this process time wise. Now what do I do? In this graph, wherever I see a head, so I imagine this graph in the form of let's say pipes. So here there are the nodes, and these are the pipes through which, let's say, some water can flow, and actually here some contagion is flowing. So these are the pipes through which water flows across these nodes, and whenever a head occurs, I say that a pipe is open, and whenever a tail occurs, I say that the pipe is closed. So let me show, let us have open pipes in green color. So let me open some pipes. So E3 is a head, and then E4 is a head. E4 is a head. I'm sorry. E3 is a head. E4 is a head, and then E5, and then E6, E7, sorry, not E7, E6, and then we have E11. Where is E11? E11, and we have E12. Okay, so all these are the open pipes, and remaining wherever I get tail, I say that these are all the closed pipes. So this is a closed pipe, this is a closed pipe, and then closed, 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 and these are the closed pipes. So we can now see these nodes as connected in the form of pipes, where the green pipes are the open and red ones are the closed. Now what it has to do with telling us whether some node was infected or not. So we started our infection over here, and we were interested in the question whether towards the end of the process this node over here will get infected or not. And now I tell you the answer. The answer says that imagine here is this water flowing from this node, and we see that some of the pipes here are closed and some of the pipes here are open. So I say that if water is able to flow from this node to this node, yes, this node will get infected, else this node will not get infected. And you can match it with what we have done previously. So whichever nodes got infected are the ones which you can reach with the help of these open pipes. So if you want to see whether some node is infected or not, let's say I want to know whether this node is infected or not, I will see whether there is a path of open pipes to this node from this node. So let's say here, and then I can go here, here and here. I see that there is a path. So yes, this node will get infected at the end. And let's say I want to talk about this node over here. So I see that there is no path of open pipes from this node over here to this node. So this node will not be infected towards the end of the process. And you see, we have seen that this entire process of the infection of different nodes in the network in an SIR or let's say SIS model without using any notion of time. So this is called the percolation model, and it's very useful in the analysis, in the theoretical analysis of such processes. And I think that by now it would be clear why we use the term percolation. We say the term percolation because it is like this water is percolating through this network, and we can use it in the modeling of the epidemic diseases.